So yes, I'll try to use the mouse a little more. We have, that's exactly right though, to get to the point on why they're calling these goodies, it's essentially fluff. So if it's fluff, what does that mean? That means that we have essentially learned what Python has to offer that is highly important, or what the author thinks is highly important. And now we're going to look at a chapter that could also be named other crap, or something of that sort, because these are essentially cool things in Python, or things the author thought was cool in Python, that he wants to infuse into this book, but had no actual position for them. Couldn't integrate them in other parts of the curriculum. And there's nothing wrong with that, because Python has quite a bit of cool shit, but I just want to be clear that none of this is integral to actually using Python right now. You already know enough to use Python, and if you haven't done your little cool whiz-bingy stuff that you want to get done with it, you're waiting too long. Get on it. And so this is both a fun chapter and a relatively easy one. Okay, mirror displays. Let's give it. Is that going to be correct? There we go. Yay. Okay.
Well, that said, it is worthwhile to learn this stuff, because if you read somebody else's Python code and they used one of these techniques, you probably wouldn't be able to understand it without seeing it once.
That is true. Something else this is good for, if they don't use those techniques, this is the kind of stuff that gives you the ability to go, what are you doing? Why didn't you do it this cool, whiz-bangy way? Okay. The goodies. All right. So one of the things that Python kind of did early on to differentiate itself from other languages is they came up with this concept that you should only ever have one statement on a line. Okay? Has anyone heard of the term statement and expression?
Yes.
Statement. Okay, we have some of the people have heard it, some of the people haven't. For those of you that haven't heard it, a statement is more or less one thing that a language will do, right, that can stand by itself. And an expression can be a component of that statement, right? So you can have multiple expressions, but only one statement on a line in Python. So what we're getting to here is, okay, now we have tips of the day that pop up. What we're getting to here is that these conditional expressions that they're showing you, if we look at this, we've seen these before, right? We've seen this stuff. If x is greater than 0, y equals mathlog, else y equals float. We've seen that. Nothing should be new about that. That's just how an if-else statement looks in Python. Other languages have the ability to collapse that into one line, right? So Python, in some sense, can do that too. But you kind of have to work around Python because it doesn't really want to work with you. So in Python, some if statements, not all if statements, can be collapsed into one line. And when can that happen? It can happen only if you only care about the expression, right? So here what we have is y equals expression, right? You can essentially...
What are you pointing at?
I'm not going to be able to do it.
Well, but what are we going to do? Tell us what
it's going to be difficult.
Can we all sit on the other side of the room?
Well, I'll give it a shot here. What we have here is y equals expression, right? And then we have y equals expression. So there's something in common, right? We're setting y no matter what. So we have two statements, both of which set y. And the only thing that's different is the expression. In this case, you can collapse that with Python. So he's making a deal about this to say that this is something that he likes about Python. In every other language, you can do this too. So what he's doing here is he's stating the statement y equals something, right, can be one line. And you can make an if expression. You can put an if conditional inside of an expression. So that's the cool thing here that he's trying to show off, right? If you're wondering why this is in this chapter, it's because he's taking an if-else statement and he's showing you a newer, cooler way to do it with one line, right? So that's a more advanced syntax that you can do to make some if statements smaller. Now, when can you not do this? You can't do it if you have two totally different statements. If you say if x equals 0, right, and then you say g equals math.log, else z equals float.nan, You can no longer collapse that. Python says that has to stay by itself. And interestingly enough, in other languages, I think this is actually easier and cleaner in the regular syntax. So let's go ahead and play around with that, and I'll show you what we're talking about here. Python 3. Okay. So in some languages, you could do something like this, right? We could do if 10 is greater than 0, right? We could do return 5, else.
The 10 is always greater than 0.
I know. It's just an example. Give me 1 second on this. Yeah, here, this is how it would look. Return 5 if 10 is greater than 0, else return 6. Okay, let's take a look at this statement here. I wanted to just show this to show you something we cannot do, right? This is what the author's trying to show you. Here we have a statement, right? Return 5 is a statement. You're telling Python to do one thing, right? Return 6 is also a statement. In Python, you cannot have two statements on the same line. Got that?
Can you just remove the second return?
That's exactly what you have to do, right? So in Python, if you can say that, okay, return is part of that statement, but it takes an expression, that expression can have an if conditional in there. And that's exactly what he's doing here. So the connection between these two is that you're returning either way. So if you remove this return, now what you essentially have is an expression. And that Python will look at it like this. So that makes sense to Python, right? And it'll take that happily. And that's what he's talking about here. Okay, so there's your nicety. Your nicety is that there is an if expression, and you can use that. Okay. And by the way, if this type of stuff interests you, like actually writing things in shorter amounts of characters or lines, Python is the worst language for this. Right? I just wanted to tell you that there's no language that is probably more needlessly verbose and picky about syntax and spacing than Python.
Spacing, especially.
Yeah.
But isn't, in general, being trying to put things in the shortest number of characters is oftentimes, I guess, not maybe that useful. Maybe it saves you a little bit of time right then, but later on when somebody reads it, your program, it's probably maybe not quite as easy to reason about, right? The more verbose version is...
Oftentimes not useful is oftentimes a better way of saying fun. I mean, yeah. It's kind of cool and it's entertaining to make things short. You're right. It's not as readable in many contexts, right? So Python has very firm rules about what you can and can't do. And those rules are not relaxed at all to make things shorter. The author thinks this is really cool because he can get this done in Python. He can essentially circumvent some of those rules. But yes. Now this is really cool here, list comprehensions. Python has these things. You will see these everywhere. And we should probably actually even open them up in the official documentation so we can see a little bit more about them. Let's see here. You know what I just thought of? I'm not recording this thing.
I was gonna say, but
yeah, please do say. It's
you're still in good time.
simple screen recorder.
Let's take it from the top.
Good class, how to record.
Okay. So here we're looking at the list comprehension syntax. This is not the right one. This is Python for beginners, and I want the actual Python docs. There we go. Hopefully this is it. Yep. Okay. So what's cool about these is Python has this concept, we kind of showed this earlier on, where we could treat things as if they were lists, even though they weren't lists, right? Like we went through, if you remember some of those examples, we went through and we showed letters, right, in strings. And we said we could iterate through those letters inside of the strings in the same way we could iterate over elements inside of a list, right? So let me come back and I'll show you a little bit about what we were talking about and what we did. We did something like, we could do A equals 1, 2, 3. And then we could do for I in A, print I. And we get 1, 2, 3 out of it. So we're iterating over an array of 3 elements like that, with that for I in A. Now that same syntax, the for I in A, will also work fine with strings. If I say A equals, and then I say hello world, and then I do this again, for I in A, and I do print I rather, we get the same thing. So we have a syntax, this in syntax. And in is doing something special, right? Whether A is an array or A is a string, in knows how to loop through it, how to iterate through it. And that's because under the hood, they implement the same interface. The array and the string implement the same interface. That interface provides very little, but it provides a method to say, get me one element, get me the next element, get me the next element, get me the next element, so on and so forth. These things can answer that call. In says, I need the next element, and whatever you're talking to, whatever object you're talking to, can answer that call, can implement that. Say, I know how to give you the next element. In a string, it's a character. In an array, it's an element, right? Now, here's the thing that the author thinks is cool about this. There's a syntax in Python where we can actually make that very terse too. Again, the last goodie was how to make Python code smaller. So is this goodie. There's nothing, there's no extra feature this is giving you. This is just a method of writing the same code you already know how to write, smaller. So let's go back and let's look at this. What we're doing here is we're iterating over A, which is a string, hello world, and we are, for every different time we get a character, we're assigning it I. Right? We can do that with the same syntax here. We would do I for A in A. That's not right. There we go. I don't know. Okay. X for X. So here. Let me give it a better name than that. We could do A equals this, and then we could say here, my car for my car in A. There we go. Right? So this is a syntax. This does the very same thing that our loop did here.
The brackets are required? The brackets are required?
The brackets are required. So the brackets specify that you can have this list comprehension syntax inside. And how the list comprehension syntax works is pretty simple. Right? The list comprehension syntax works in a way in which you can iterate over every single element in that container, whether it's a string or an array or whatever it is that implements that interface, right? And every time you do it, you can change it, right? So if you look here, we say my car for my car in A, right? What we're doing is we're iterating over A, and every time we iterate over it, we're assigning a variable my car for that element. And now I'm just returning it here. But I could also do this. My car plus, over here. Now what I'm doing is I'm returning the same list up here that I had before, but I am prefixing it, right, with this character. So I'm actually taking every character in that string, and I am changing it in the new list, right? So if we do something like this, we just get all of the elements of it back, but I can change it. I can say something like this, and now I'm changing what each and every element is that comes back. This is just another way for iterating over something and changing or modifying that value. Ed?
I think the key takeaway on this one, though, is that with for loops, normally you would have to put the block around your constructed extra string. And that this is a syntactical way of putting it all in one line.
That's also a good point, right? So that's totally valid too, right? With the for loop, if you look at what we're doing here, when I said for I in A, and then I said print I, you can see I'm not actually returning a list. I'm doing something every time we iterate over it. But the list comprehension is returning a list, right? So yes, it works inside of a bracket. It's a syntax inside of a bracket. But it's a syntax inside of a bracket because you're constructing a list. So when you iterate, you can do anything with it. You can print things out like I'm doing, or you could do something like this. Let n equals this. Damn it, JavaScript. N equals this. And then I can do for I in A. N dot append I. Right? Now if I look at n, I get this. Hello world. And it's all inside of a bracket because it's a list. Right? That would be the same thing as me doing this. N equals, right, I for I in A. They're the same thing. Now do you see them both next to each other? We have, on one case, we have the for method of doing it. This is the iterating method. Like Ed said, we have to create the list ourselves in that method. We're creating a list outside of it, and as we iterate through that array, we're appending one element into that list. In the list comprehension method, though, look how much smaller it is. Now all I'm doing is saying n, and I'm putting inside of brackets, I for I and A. Right? For each different element inside of that array, I just want to make a list out of it. Okay, there's a bunch of eyes like looking at it. You'll see this oftentimes in languages that are more functional than Python. Most languages don't have this syntax, though they should. JavaScript just got it. So yeah, this is kind of cool, but again, there's nothing special about this. If you understand this method at the top, this for loop better, you can use this. There's nothing wrong with that. It does the same thing. This is just another syntax to do it. So I'll show you one other thing too here. If I come back and I do this for loop again, we set n equals an empty a new list, and then I say for I in A. Now I can do this, append Now if I look at n, I have all of these things. I'm actually isolating each different character individually. I'm prefixing it with characters so you know what it is. That is the same thing as what I had earlier. That's the same thing as this. So you can write all of this code here, n equals an empty list, for I in A, n dot append, you're adding a new element to it, and you're doing this, you're changing the way that element is getting added to that list. That is the same thing as this syntax here. And if we look at it, what I'm doing here is I'm saying I want to create an array, and I want that array to have this. The character prefix with my character, and I'm getting my character because I'm assigning my car for every element in the array. These are just more terse ways of doing this. So if you're interested in the syntax, it's called list comprehension, and I'd highly suggest checking it out on the official docs because there's way more to it than what the book is giving you out. So look at this type of syntax the docs have, right? Let's look at this here really quick, and I'm going to show you. This is how you can make very terse Python code. And I wanted to go through this one because it's amazingly, this should show you how powerful this type of syntax is.
Can you go back to the previous?
That's you? Okay. That's my laptop does that too when it's about to die. So that's a red alert.
Can you go back to your terminal for a second?
Yeah.
Here.
Okay.
Okay. Thanks.
Okay. So what I wanted to do here is when we look at something like this, how do we parse this, right? Well, what we have here is we have two list comprehensions sitting inside of each other, right? Now this is where it gets kind of complex, right? What we have is this if statement is new. It's called a predicate, right? So the predicate is actually a way where you can select certain things. Let's say you want to select all odd numbers, right, between 1 and 10. How would you do that?
With the percentage divide thing. Right?
Well, the
modulo.
right? Okay, so we can use the if statement here to determine that, right? So let's take an array. is that? What is popping that stuff up? I created a new session so I can use just the presentation for this. Let's see here, creating a sequence in Python between numbers. I thought it was sec. Range, okay. So what we can do here is we can use this range, and we can say here x for x in range 110 if x is less than or x mod 2 equals 0, right? That's going to find all even numbers between 1 and 10, right? Now if I remove this, you can see something else. You can see exactly what numbers it's iterating over, 1 through 9. That's why 10's not there. So range is not returning the last number you give it. It's exclusive to that. But here's a syntax above where we're finding all even numbers between the range of 1 and 10. If we look at this other thing that we have, here, we're doing the same thing. We're saying for x is not equal to y, right? So when we take this and we say that, let's see if there's an easier one than that, slightly easier. Here's another one here. This is where they're squaring things. So if you see here, we're taking x in range 10, right? That's the same thing as range 1 through 10. Should be anyway. Nope, range 10 has got 0 through 10. So range 0 through 10 and range 10 are the same. Those two things return the same thing. So here's what they're showing you. They're showing you that you can find the squares of that by changing the first number, right? Now we're finding all squares of the numbers that are between 0 and 9, inclusive. Okay, so what we have here is, let's just go this one more time, and I'm going to skip that last example because this is very difficult to explain. Can I come over here? Are we good on this side?
Yeah,
Okay,
go
good.
for it.
Look, here, we have projections here.
Best of those people now.
This is called a projection, right? This guy here is called a projection. So this is essentially how you want that element to look on the new list, right? This is simply the iterating statement. So we're giving this range 10. That's an iterator, right? That's returning an iterator. It's saying, I want to create something, and every time you call me and you say, give me the next element, I give you another element in that sequence. And then the thing that you're providing here, 10, is when you say, give me the next element, and range says, I have no more. That's all there is to that. So range is essentially an object that has an ability to give you an element every time you call on it. When you create the range, you set what the highest number is in that range. And then when you say, get me the next element, it just provides you another element. So we're iterating over the range, we're assigning every different thing we get from that range, x, and then we're changing that projection over here to be squared. So that's going to show you all squares that are in this range.
Is that word projection, is that a generic term in programming?
I think it's a math term. That's probably that question. I think it's a math term.
If it's a math term, it's not one of the dialects of math I understand. I think it's just a range.
There you go.
Uh,
Have you heard it before?
Only in 3D math when you're doing like rotations and worrying about movements and stuff like that.
You've heard the term before. Where does it come from?
Well, like you said, geometry.
What?
Geometry.
Geometry? I don't know. Anyway, yes, that's the word I've always heard with list comprehensions. Let's see where I got it from and making sure that I'm not making it up here. List comprehension projection.
It seems to fit, but it seems like you're pulling up primarily Python references when you say projection.
Well, list comprehension will generally go to Python references.
Let's see what Python actually calls it. Do they have a name for it? List comprehension. Python doesn't provide us another name for it. So my name, though, may be very good. And I have no idea where I got it from. I don't make any claim that it's the right name even. Nope, no idea. I think it's a Haskell thing, but I'm not even sure on that.
It's,
Hmm?
you have the domain and then what it maps to. So it's a projection from domain to the new set. This is two sets projecting to each other.
Is that the right name though? Is that like a math term?
Projection. Set.
It's probably the term for what's on the other side of the map.
Yeah.
In set theory, a projection is one of two closely related types of functions or operations, namely a set theoretic, whatever, operation typified by the jth projection map written. There you go, projection,
Okay.
set theory. Comes from set theory. No idea why I used it. It could be totally wrong. Ed,
No, it's just because the jth thing indicates sets of sets.
well, this comprehension does return one set when given another set, right?
It's like a map.
You're taking a set, you apply a transformation.
No. This is presence inside a set. This is if you want to do math on whether things are in sets.
Okay, I'm happy with the term anyway, whether or not.
Yeah.
By all means, if I'm wrong, someone should just tell me. I got it from this thing though. So
if you can see also, maybe it's relational.
a projection is a mapping of a set or other mathematical structures into another subset or substructure which is equal to its square for mapping composition, or in other words, which is idempotent. There we go.
Idempotent to my friend.
Idempotent. There we go.
The
That's
basic
Wikipedia's
idea
way of
is
telling you to go
yeah.
fuck yourself.
Oh.
Okay. I have no idea what. I actually know what some of those words mean. I actually know that. But I will say this. I will say this. I have never heard idempotent once outside of reading it. That was the first time I've ever said it, and I never heard it before Ed. So yeah, there's my brownie point. It's idempotent. There was another time I did that too. Idempotent?
Yeah, it's a soft dot.
Idempotent. Okay.
It basically means.
We got head nods on that one, so
It basically means like you know how you do the math equals comparison.
right.
Okay,
Yeah.
and therefore you can like say x is 5, y is 5, z is 5, but the idea is 5, and there's only one 5 idea. That 5 idea is an idempotent idea in math.
I want to show you something. This is
Lots
where
of hits,
because some people don't know where this came from, and that may have seemed just like senselessly obscene without some examples. So there's a language out there called Erlang, and it's actually a relatively fun thing. But here's what we have here. This is a comic called Fault Tolerance. So this guy says, so how do I query the database? And the guy says, it's not a database, it's a key value store. Okay, it's not a database. How do I query it? Right? He's just trying to get a job done. And you meet a lot of people like this. You write a distributed map reduce function in Erlang. And then the guy says, did you just tell me to go fuck myself? He says, I believe I did, Bob.
I think I've seen that.
So that was a popular one for a long time. And the background of that is everyone used to use databases forever. And then when these things, NoSQL came out, and everyone was all hyped up about how they were going to save the world and whatever, people jumped on them. And the reality is that all those NoSQL products are more difficult to develop with than SQL. Many of them anyway, right? Especially when you're writing this map reduce stuff. Way more complex than a SQL query. So everyone was feeling this comic.
This might be going too far into that hole.
Yeah.
But if there's
Why
like
stop it?
You only got one chapter.
You're right.
do a Google search for SQL to MongoDB translator
Yeah.
and just run the example, and you'll see the difference between SQL and their SQL.
Yeah, it's probably horrific. But the point is, this was something that hit everyone's core. I'm not actually going to do it in class, but I suggest other people do it too. Because I made a reference to this comic, and then I was like, shit, not everyone's going to understand that comic. But all techies have seen this. Did you have something to say in the back? Okay. So yeah, that was fun. And then that was just me reading the okay. So we have list comprehensions, these guys. And again, this is just a different syntax for the same type of thing that we already know, right? It's fancier, it's jazzier. I do suggest you learn it. You'll see it in a couple of other languages. It's not unique to Python, and it is pretty cool. Here's one more he's got, which he's using to select just the uppercase letters. So remember we had this if here and we called that a predicate. Now the predicate thing is much less so than the projection. A commonly agreed upon way of what we should call that is upper is a predicate, right? That means it's simply telling you whether or not this element you're feeding it passes this test. So is upper is going to return true or false if it's uppercase. It returns true, otherwise it returns false. And what we're doing here is we're saying that we want to iterate over all of the elements in T, right? So for all of the elements in T, we're going to iterate over them. We're going to assign S to each one of those elements, and we're only going to add it to the array if S is uppercase. So if you give this thing a string, it's essentially going to return you a new string with all the lowercase letters removed. Not going to touch the original string. Okay. Generator expressions. So these are, again, this is like this book, this part of the book is not in any order whatsoever, right? So we talked about this concept of iterators, right? And I said an iterator you can use in this for syntax, right? You can use it for list comprehensions, right? Well, a generator is essentially it's a method of creating an iterator, right? So I said an iterator is something that has this interface, which you can say, give me one more element, right? A generator does the same thing. Generator is a subset of iterators. So a generator, right, here when you put these parentheses this time, and not the exclamation points, you can actually create a function, right, essentially, and that function gives you the ability to get the next value. So if you wanted to see how this works under the hood, right, this is one method of doing this and creating this type of thing. And this is the interface here, next G. Right, so if you look here, you're going to see where they're calling next G. Here we create a generator, and to get the next value from the generator, we simply call next, and we give it the generator. Right, this is what for is doing under the hood. This is the same type of thing that for is doing under the hood. So that for syntax you're seeing is simply saying, give me the next value. And with a generator, it's that explicit. Is this making sense to you at all?
One more time.
What's up? One more time?
Repeat it one more time.
Yeah. Okay. A generator is a function, right? But most functions you have can return how many things? How many times can one? That's right. You can only return and then you're done. Right? And when you call the function again, it doesn't know where it left off. Right? So most functions return once. Generators don't. Neither do iterators.
Did we cover the yield keyword?
No, and the book didn't either. I'm wondering if I should get into
It
that.
seems like that's a better way of explaining it than just throwing. This is basically like just shortening the syntax.
Yeah, it is. Yeah, let's go ahead and find an example with that. Okay. So rather than showing you just how it looks to for, and I don't know where these key bindings are coming from, but they're super annoying. Okay. We're going to show the internals of how this generator works. Generator Python. So most functions, when you're done with the function, you give it return, right? And when you return from something, that's it. The function's done. Generators don't return until they're complete, but they have another keyword called yield, and that keyword looks like this, right? So here's one example of that keyword. We talked about how you, and this, by the way, this is the first n, right? This is exactly the way range works, right? This could be the implementation of range, right? So first n takes a number, n, and it starts from 0, and then while the number is less than n, what it does is it yields the next number, right? This yield thing is what's new to generators, and this is what makes a generator a generator. You'll see generators in many languages. The cool thing about this is when you yield the number, the generator is done until you call next again. So if we saw this here, and I know that this is a little bit more difficult, there should really be a whole chapter on this, but there's not. So we're going to work around it. See how we say next here? We say next G, right? When we say next G, this function resumes. And it does it one more iteration until it gets back to the yield. So when we say yield number, that's the first time that that function's done. And now it's not going to do anything until you call next again. And when you call next again, it resumes where the yield left off, it adds 1 to it, and it comes back up here, and it yields 1 more time.
I don't get where you said the next. I mean, it's just implicit.
The next is over here. So the next isn't something the function does. The next is something that the person calling the function does, right? So the next isn't inside the function. The yield is inside the function. So see, like, look up here. When we say G equals and we have this thing is a generator. Robert said, hey, that's a very complex way of writing a generator. Maybe we should show how a generator really looks, right? And that's a good idea. The book doesn't do that. This is a complaint that I would have against the book. So how does a generator really look? A generator really looks like this. This is what a generator really looks like. You have def, just like any other function, but you have this new really cool whiz-bangy thing called yield. And what yield does is it returns. But when you call next on the generator again, you resume where you left off, right?
If you really want to go without the benefit of the yield keyword, because that's a feature of that, then generally what you would do is you would have like a generator written maybe as a class or something with a get next value. And you would just basically get next value instead of actually, treating it like a value. You would just simply ask for the next value of this or the next value of that. But that would be if your language didn't support making it look a little cleaner and making it look more like you're reading a data value.
Yeah.
Some generators are some are finite.
Yes, that's another point too. So we have this idea here that this generator will eventually complete. It is not necessarily true of all generators, right? The real cool thing about a generator is when you say you want to have a list with elements 0 through 100, let me tell you why this is here. What the computer does is it will generate the list with 0 to 100, right? And you have that in memory. And then every time you iterate it, you're iterating over one of those elements, but you have this full list in memory. The cool thing about a generator is you don't have to have everything in memory. The generator can go to the database to get the next element. The generator can return to you one element, and then you can forget it when you're done, and it goes away, right? So the generator doesn't have to be finite to begin with. The generator can return all of the numbers that there are, and just every time you call next, it returns a new number. You can have an infinite series in a generator, right? You can't return all of the numbers in a list because you simply don't have enough memory for it, right? At some point, you exhaust all of your memory. The computer goes, crap, can't fit 100 quadrillion billion, and then you out of memory, your computer crashes, program crashes, right? A generator can keep saying, I'll give you the next one, I'll give you the next one, I'll give you the next one, right? Okay, so this is the catch. To get back to it, yield is just like return, right? Except you can resume it later. If this was a return instead of a yield, it would work the same way for the first element. What would it do for the next element? Crap out. Because you can't do anything when the function's done, right? But with the generator, you can always call next. And that next is how that works. So he's saying that generator expressions are one of his goodies, right? Generator expressions are really cool. You can do a lot of really cool things with them. Unfortunately, there's a lot to them, and there's a lot more than this book is telling you, but this is like your little teaser. If you want to do something in a sequence, you want to return a sequence, you can use a generator. If you want to do things like paging, like you see the website, and you hit the next button on the website, next button on the website, that can be a generator. Every time you hit the next button, right, it can go back to the database, get you 10 more rows and return them. So next can do things like that, database access. Yes, you have questions in the back?
Yeah, if you wanted to be infinite, what would you put instead of range 5? Like if you wanted to go forever?
You'd have to actually create something that represented infinity.
Like
Or
an arbitrary large number or something? Or
no, you could use something like not a number and float, or you could do something like infinite range, create something named entirely differently. It takes no arguments and does that.
You could create a generator that just basically uses like a big number library, so you're not constrained by the size of the storage, and just keep telling it to add one and return the next.
Yep.
Yeah.
So again, this is, I know I'm kind of losing a lot of people because I'm jumping between advanced topics, but that's how this chapter is assembled. So remember, keys for generator. Remember what I told you about recursion? We hit on recursion a little bit. And I said recursion, you always have to be approaching terminal case, right? You have to you have to approach something in which you say, I'm not going to recurse anymore. And I told you that's kind of how you always want to think about recursion. So a function can call itself, that's totally fine. But at some point it has to stop calling itself or you're not going to do anything useful with it. That's recursion. Now with generators, here's what I would tell you. Here's your take home for generators. If you want to create series of something, right? Like you're doing a next button for a result set or something like that, that could be a generator. If you want to do something for an infinite set, that's a great example of another generator where you can just want to have an interface where you can always say, get me the next thing, get me the next thing. That's a great example of a generator. Anytime you have a function and you say, man, I wish I could do something after it returns, or what if people call it again? I want to have it provide another answer. That would be a great case for a generator. All of those types of things are applications for generators. Okay. Any and all. These are actually simple. Okay. So here you can relax for this one. This one is very cool and very easy. Let's take it here and we're going to show you, let's say that I create a function, right? And I'm going to create a function which returns true if the value is less than 10. Right? So I'm going to say def lt10 x, and then what I'm going to do is say return x is less than 10. Right? Now what you're going to see here is if I call lt10 and I give it 5, I get true because it's less than 10. If I give it 15, I get false. That's pretty simple. Right? Now I'm going to create another function for is odd. Right? Def is odd x. And then what I'm going to do here is I'm going to say x mod 2 equals 1. But I'm going to put a return there. Return x mod 2 equals 1. Now if I look at this, I can say is odd 2, false, is odd 3, true. Now, what if I want to find all numbers that are both odd and that are less than 10? How can I do that? This is where all comes in. So watch this. Def, right, lt10 and is odd. By the way, that's horrible caps, but bear with me. Now if I take that, I can say here, all is odd x is lt10 x. Now I've created a function that combines both of them. So now if I call lt10 and is odd, and I give it something like 7, I get true. And if I give it something like 17, I get false. So this is where any and all comes in. Oftentimes, I told you we have a word, we had this projection word. Everyone didn't like that word. I guess some people did. I like that word. We had also predicate. And I said there's no disputing predicate. Predicate is everywhere. You take a value, you return true or false, you are a predicate. Right? This is one of the methods in which you can take your predicates and you can either say, I want to make sure that you match all of these predicates or any of these predicates. So you can take these very little concepts like, is it less than 10? Is it odd? And you can say, I want to combine them to make something new. Now all I have to do is use lt10 and is odd. Like that's one function. I can give that to someone. So this is a very core part of functional programming. It's taking these very little things and building up something that's bigger with these types of components. So you'll see this, by the way, every language has got something that's providing these. And any, it's either provided by the language or a library that everyone is using. Okay. By the way, any works the same way. The only difference is it only looks for any of those elements to be true.
Could you go back to the console again? I was just trying to copy
Yes.
the last part.
How about if I copy and well, wait a second. Can I do that? Do.
Oh, in the Discord?
Yeah.
Thanks.
No, I can't do that. I should have looked at that before I started the class. It's complaining because I have probably Discord open on my other session. So, okay. So, any and odd are very simple. And let me tell you something else that's really cool about any. Right? Let's say that you have 20 different predicates in there, and one of them returns true. It doesn't have to evaluate all the others. right? So that's also kind of cool, is that it's smart enough to say, I'm done. This is true. We're done.
Same thing with all and false.
That's exactly right. If any of the elements return false in all, then false is done. Then all is done, because it doesn't have to test everything if it knows it's returning false. Now, here's the sticker question, because I have stickers to give away now.
Whoa.
Okay, don't say it, Robert, because you're out, because I know you got it. Does anyone know the rule for that? Oh, no. Does anyone know the reason for that? Is there's a law.
It's a law.
The law about why you can stop so quickly.
Yeah, a law about why you can rearrange these.
De Morgan's law?
You got it.
Well, yeah.
There we go.
Very specific. What was the question? Boolean algebra in general.
What's the
What
law?
was the question?
You want to say it one more time?
De Morgan's laws?
There you go, De Morgan's law. So the thing is like.
Well, if you have a multiple input and
So
if you have
this-
false, it's all false.
So the fact is, I told you that any, right? I said when you do any, the first one that's true, you're done, because you know it's true. The corollary of that is that when you do all, the first one that's false, you know it's false. You can rewrite conditions to be the opposite. You can negate every individual condition, and these are the same things. Watch this. If I do something like any, right, and then I do false, false, true, false, right? I get true, because one of them is true, right? The cool thing about that is I save evaluation. I don't have to do this. You can negate all of those things and do all, right? So you can do all, and then you can do not false, not true, and then you negate that too, right? One more time. There we go. So those two things are the same, and that's De Morgan's law. So compilers do this type of stuff. So anyway, here, pass. You want the Linux one?
Sure.
Pass that one back to him. He gets that one.
Thank you.
And I knew Ed already knew
I
that.
think these two should get one.
And Ed, you already have one, right? I mean,
It's a penguin sticker?
it's a penguin sticker. You want to? These are like high class, highfalutin penguins. Give one to the professor back
It's not
there.
it's not coming from my personal stash of already collected penguin stickers.
You got to win it.
Yeah.
You got to win it. That's it. Ed gets one because he sacrificed every other Wednesday for months. Okay.
Try years.
I think one thing pointing out is not
Yeah.
a penguin sticker, but a tuck sticker.
That's right. Tuck
That's
sticker.
really scamming.
You lose another sticker. Give it out to somebody.
Oh man.
I haven't kept any of them. I'll have you know. By the way, these were all donated. What was your name one more time? Danish. Danish donated these. So
Thank you, sir.
thank you. Give a round of applause for this. And I got plenty of crap to give away for people that can answer obscure trivia questions. Okay, I'm just making sure that these are new people to answer obscure trivia questions because Ed actually knows all trivia in the universe. Okay. Oh, this is we're back
The
in.
answer is B.
So what we're gonna do here now is any of these. Okay, so we went over any. Here's another example of any. Okay, that's stupid. Any all sets? Sets are one more thing. Yes, Ed.
Can we pause since we're on a new
Yes, that's right.
section?
Pizza. That's exactly right. Thank you for that. All right, guys. So we had the question earlier on about this whole rewriting ands and any's, and this is where this comes from. So I didn't really want to go into this too much here, but I wanted to give this as like an outside reference for those that are interested in this type of stuff. This is methods in which you can use to rewrite Boolean logic. So this is definitely worth giving a look the first time, or 2 or 3 times. It's pretty cool stuff. But I'm not going to be killing that today. So what we have is a couple more goodies here. We used dictionaries earlier on in this class as a method, and you'll see this in a lot of dynamic languages, as a method of ensuring that keys are unique, right? So we don't care about the value. We just need to make sure that we have a unique list of something. You often will just create a dictionary, right, and set the value to something like none or whatever. Because then you can track the keys and you can make sure the dictionary you know in no language allows duplicates. So if you're using something like Perl or another language that doesn't have sets, you can use their hash or their dictionary, their associative array, and you know that you can never insert the same thing twice, right? Why? Well, if you go to a dictionary, let's say that you come over here, right? Let's make sure that everyone's awake and we're all back from lunch and thinking Python. If I say here, my dict equals, and then we're going to give it something, foo 5, right? That's a dictionary. It has a key foo. It has a value 5. I go my dict, you can see that. If I go my dict foo, I get 5. If I go my dict foo 5 equals 42, right? What is my dict going to have?
Add a new entry?
No.
Overwrite?
Overwrite. That's the same behavior
That's assignment, yeah.
in most every language, right? So if I look at my dict again, you see I overwrote the 5 and now I have a 42. This is how you can be sure that you don't ever have duplicate keys. Because if you reassign with the same key, you simply rewrite the value. You overwrite the value. Right? Does that make sense? I'll say it again. You have a duplicate, you have a key already in the dictionary. You assign again to the same key. You don't get a duplicate key, you overwrite the value.
Okay, I'll take that. I see what you're saying.
Okay, so because you're overwriting the value and not adding another entry, you can be sure you do not have duplicates. That is true in Python, it's true in PHP, it's true in Perl, most languages. That's a very good idiom you can stick to.
What about where the dictionary is immutable?
The dictionaries are not immutable. You
Okay.
can always add, well, there's,
Well,
in
I meant-
Python, there,
I meant where a key is immutable. Is there such a thing as dictionaries where
So,
all of the keys have to be immutable.
in a
But
language
you
that
just-
has an immutable dictionary, the keys will still be a set.
that's right, but here you modify the key.
I modified the value.
Well, okay, you have the same key.
map.
Right,
However you say it, that key was mutable.
yes,
The key did not change.
right,
Foo
I'm-
is the key, and the key did not change.
right. Foo is the key did not change. The values are
Value change, I'm
mutable.
sorry, that's what I meant.
Right.
Value change.
The values are mutable. So in Python, all of the values in the dictionary are mutable. That may not be true in other languages. So in Python, when you write to the same key, you mutate the value. You overwrite the value.
So, at the risk of being overly pedantic, there's the key, the value, and the mapping. And what you're changing is the mapping, not the key nor the value.
You can think of it like that. That's perfectly fine too. You can think of every value in Python as being immutable, and then you're just changing the mapping. Yes, that's perfectly fine. So if you want to think of it like that, and that's actually the way it works under the hood, usually, but not always. But what would happen is, okay, so think about it like this, Peter.
No, it's all right. It's me.
But-
It seems to me that if foo were immutable, you could not say it used to be 5, but I'm going to have it be 42, because that's new.
But the 5 still exists in memory,
Yes,
and it
yes.
hasn't changed anything.
No, but it's not connected to foo anymore, so you've been.
The mapping has changed. Let me give you this as an example. Right, by the same token, Peter, if we have something like this, and I say variable, right, equals 5, I can later go variable equals 42, right? You see that?
Yeah.
So when I did that, I didn't, the variable, that 5, is still immutable. I'm not overwriting that part in memory. I'm rebinding 42 to the variable.
So what does it mean if a language tells you this, whatever is immutable and x equals 10, and you're at liberty to say x equals my mother-in-law, then what is immutable? I mean, I'll just put that way. Can you give me an example of an immutable?
Let me give you a visual example, because I think what's happening is, you're right, something is changing, but what is changing is not the thing we're talking about. Okay, so we've got over here this set of keys,
Right.
and inside of it is foo.
Right.
And over here, Evan started off with, I believe it was 5?
Yeah.
5 and 42, and these are sets of values. or both. And foo has a mapping to 5 when he says that foo equals 5. All right? And then when he reassigned it to where it was 42, this old mapping is gone and the new mapping to 42 exists.
But isn't that what altering something amounts to no matter what you're doing? Isn't that how you mutate a variable?
Well, what you're doing is, notice that I've used the word mapping
Yeah.
to talk about these parts.
That's right.
All right? Okay? And so the mapping mutated, all right? But the number 5 didn't mutate because 5 just means 5.
Right.
Whether you're using 5 fingers or 5 anything.
Right.
The number 42 didn't mutate because that also is a constant, it's 42 however you think of it. The key foo did not mutate because in his changing of the mapping, he did not wind up changing the text FO.
I see it, and that's very, very helpful with that extra variable. But then, what does a language which claims to have immutability as importance, what does that mean if nothing, if you can change everything and it's still immutable, what is immutable?
No. We're not saying that dictionaries are immutable. We're saying that the mapping.
That's right. But I mean, what if languages talk about mutability? I'm sorry.
Let me give you this as an example, right? Because Python calls.
If everybody gets this, go ahead.
Yeah, no. Let me show you. Let me give you a quick example here. We have these things in Python, right? Which essentially we have lists 1, 2, 3, right? And with that, I can assign that to A, and then what I can do is I can say a.append 4, right, or 5, and you can see a change. But likewise, if I have an actual set and I say b equals 1, 2, 3, there is no b.append, right? It's stuck like that forever. That's immutable because that set equals those 3 things. That tuple equals those 3 things, and those 3 things can never be expanded on. Now here's the catch to it. If I put, just to totally blow your mind and to hopefully make this clear, if I put a list inside of that set, now I have something immutable inside of something mutable, right? The list is immutable. Can I add to it? Yes. Right? So watch this. If I say here b equals 1, 2, 3, 4, like that, right? Or an empty list, I can actually go b 1, 2, b3, b3.append. And if I look at b, you see here that I have 1, 2, 3, and I have a list with now 1 element in it. You do have a very, sometimes it can be confusing line between immutability and mutability. But the reality is that in this case, the values themselves are immutable. They're stuck in memory and nothing's going to change them. But the bindings themselves are immutable, and you can change them.
The bindings themselves are
I'm sorry, the bindings, I said that backwards. That's right. The values themselves are immutable in memory. Nothing's going to change them. The bindings are mutable, and you can change them.
So when you got those parallel programming where you got all these different channels and things lined up next to each other, and you want to be careful that a value doesn't change as two people are working on the same thing, that's a kind of mutability problem, and this is the way it's defined.
This is just the way Python does it. If you're talking about other languages, yes. In some other languages, everything is immutable. You can't reassign to a variable. Haskell would be an example.
Yeah.
If a equals 5, a always equals 5, and nothing can change it. But that's not Python.
Okay.
So Python, this is what this means. And you just got to kind of work with it. Because it's not the same concrete, this thing will never change, the binding can change.
Yeah.
You know? Okay. And not just that, but the types can change too. Which, Ed tried to clarify in the last class, right? We talked about it. He said these are the way that Python describes itself. Python is dynamically typed, and it says it's strongly typed, right? So that means that you can change these bindings, right? But that the functions themselves should only operate on one type. No, I said that wrong. you can change the types of the variables, but how does Python define strongly typing? What do they say? Give it a shot, Ed. I don't know.
No, it's
Some people argue this, by the way. I'm inclined to agree that they're wrong too. But what do they say? What's the...
So basically, because all of the operations hang off the types, you cannot call an operation on something because it does the runtime type checking. So it's really doing type checking, hence the strongly typed. But it is not... Wait, is it strongly and statically?
Okay, we're going to ignore this because these are words, right?
It's dynamically typed. It's
dynamically typed, but also
it's strongly typed because it does all the checking at runtime.
Look, the reality is that, in my opinion, we got into this whole dispute last time, right? We talked about polymorphism. We talked about people have different definitions of it. You can read the Wikipedia definition. You can listen to someone who comes from object orientation talk about the definition of polymorphism. You can read the book's definition of it. These are words. Different people define them in different ways. You just got to deal with it. I prefer not to use them with the same passion that some other people use them with, because simply I don't care. But I promise you, Robert made the argument Python is not strongly typed. If you really want to read something in using, go listen to people who are passionate argue with Python people that their language isn't strongly typed. It's a lot of fun, but it's not my idea of how to spend a day. But yes, there are disputes around these words, and you can raise that dispute as well. But in Python, when they say immutable, they are not referring to the binding. They're referring to the value. Okay, and that's all there is to that. So sets. We talked about this idiom with dictionaries being used to eliminate duplicate keys. Python has a better way of doing that. You can have a dictionary in which every key matters and every value does not matter, right? If you find yourself in that predicament, saying, why am I assigning values to these keys when the values don't matter, you should be using a set. And Python has them. So if we look here, this is one of the goodies for the language. I actually like sets. I like languages that provide them. There's certainly advantages to that. You'll see that Python has another built-in type called a set that behaves like a collection of dictionary keys with no values. Adding elements to a set is fast, so checking membership, so is checking membership. And sets provide methods and operators to compute common set operations. So if we... I hate these hotkeys.
He keeps opening that window.
I keep pressing the Windows key, and the Windows keys on Xubuntu, they all do something special, like by default. And for me, that does something different, and that's throwing me off. Okay, so what we do here is we're gonna reset it. We're gonna say A equals set, right? 1, 2, 3. A. Now I have a set with 3 elements in it, 1, 2, and 3. What happens if I do this? Now I have a lot of elements in a list that I'm providing to set. What happens? They go away. In a set, you can never have duplicate elements. Remember what happened in the dictionary? In the dictionary, when you provided another assignment operation to a key that you already had, you simply overwrote the value. When you create a set with an additional element which is already in the set, you do nothing.
But the element is the list, isn't it? You have one element in that set, which is the list.
No. The set in this case, so the set is a constructor in this case, and the constructor is taking a list. But that's not what the set is.
Okay, all right.
That constructor takes a list and it creates a set from that constructor. That's an important point. You're not making a set with just the list in it. You're making a set with all of the elements in that list. And if you provide a list with duplicate elements, because you can have a list with duplicate elements, if you provide a list with duplicate elements, they simply go away, because a set can't do that. It's not what they're there for. Okay. Yes?
To do what he wanted, you could do it by adding a couple of brackets.
Let's not do that. But there's always a way to do stupid things. So
Hiding.
Okay.
So the value is either present in the set or is absent in the set. And there's no in between.
That's also good. Ed, speak up, because that's fine. I'm saying that's a good way to think about it too. I like what he just said.
Think of sets as presence of a value. A value is not present 3 times. It's either present or it's not present. So it's either in the set or not in the set. So if you add it to the set 3 times, it's still just in the set. Okay? Whereas if you remove it from a set, you haven't removed one of the times you set it. You've removed its presence completely. So it's completely gone from the set.
That's exactly right. That's another way to think about it.
You know, we use it in the 4D data, in the database terms. Certain databases, the sets that I've used, they're just like pointers to records. They're not, and it's all the characteristics that you described so far. But I think when you say sets, I think of them as, in terms of database sets. So you can have a selection of data. Maybe there's 1 million records in a table, but you've selected 50. You could have a set. You could have that set and recall that set of that 50. It won't be an ordered set, but it'll be the same records. And subject to change, of course.
Yeah, that's all right. And I wanted to show you this here. When you look at a dictionary in Python's help, right? You'll see here that some of these things provide a set-like object providing a view of D's items, a set-like object providing a view of D's keys, right? The reason why it's providing a set-like object providing a view of D's keys is because D can never have multiple keys by the same name. So if you call keys on a dictionary, you're going to get essentially a set-like object back because you can't have duplicates. So it's just going to tell you what's present and what's not present.
Can the dictionary have duplicate values?
That's a better question, and I don't know why they said that there. Like it wouldn't.
A dictionary can have duplicate
It can,
values,
yes.
You could have 2 keys
Yeah.
referred to the same value.
But he's referring to the words that
Exactly.
they're using.
So how come?
Okay, look here. So let me say this here. The values thing doesn't actually say a set-like object. There's your point. If you call d.values, you get an object providing a view to D's values. You don't get a set-like object providing a key to a view of D's values. And if we look at the okay, so the question is, what's the difference between D's items and D's keys?
The item may be both, key and the value.
There you go. That's exactly right. Okay, that's right. So d.items or mydic.items. There you go. That's right. Okay. So what we're doing here, I was just showing you that in the documentation, when you call d.keys, the dictionary.keys, you are getting a set-like object back because you should think about these as the same way. You can abuse a dictionary to work like a set, and the man pages, the documentation for it openly says that. You know, you call d.keys, you get a set-like object back. You don't have to do that, though, because Python provides you an actual way in which you can use sets directly. And you just use set, and you can provide it a list. Right?
Are sets ordered?
There
yes.
can be ordered sets, but in general they're not.
I believe. Let me see here. 3, 4, 1. Yes.
In Python they're ordered.
In Python they're ordered, which is, I was about 95% certain on that, but now I'm 100.
That would be
Okay. So counters are the next thing that we have, right? And if we look at counters, what can we do with that? Well, so counters are returning to you the amount of times that that element exists in that list. So you see here, he's saying from collections import counter. You actually have to import something to use a counter, right? Then what you can do is you can provide counter in the constructor, right? So this is the constructor for counter. You can provide it something, and when you provide it something, it's going to tell you the count of how many times those things are there. That doesn't sound to me like something you're going to be using often, if at all. But that's one of the author's goodies.
Yeah, a set and a counter is how you make a histogram. So all the data science geeks need to know those 2 things.
There you go.
Yeah.
Yep. That's an area where you would use this if you're making a histogram.
It's a shame
Good
we didn't
point.
call it histogram instead of counter.
Actually, I think you're right, because that would make a lot more sense in my opinion. Like the way that it's outputting that I think that's a much better name for it. Yeah. When I think counter, I think of an object that has an increment and a decrement or something like that, and that's it. Okay, default dict. This is pretty stupid to me. This is, if you thought the last one wasn't all that useful, this one's going to blow your mind. So this one, this goodie has essentially the ability to create an object that wraps another object. And then if the key in the object you're wrapping isn't there, it adds it to itself and it shows it to you. And if that doesn't make sense to you, it's going to be hard to work with it. We're going to show it to you here. So what he's doing here is, if we look at this, and I'm going to try to use the mouse. I'm going to behave. We look here. We're importing from collections this thing called default dict, right? We're providing it a list, right? So we're giving it something, and then we're saying D is equal to that default dict object, right? So what we can do now is we can say D and then new key. This is something that is not in the original list. That's why he's calling it new key equals T. And we can modify T, and we can say T.append with a new value. But where does that stuff go? It goes right here. You see it at the end of the object, right? So it's not actually in the class that you're providing to the constructor. It just gets added to the object outside. So what is this used for? You can use this if you want to wrap someone else's code. They're giving to you an object, and you want to add some stuff to that object, right? But you don't want to muck with their own thing. You want to do this yourself. This is a tool in which can help you do that, right? So essentially, when you call something inside of default dict, it delegates to the class that you provided up here. Delegate means it says, do I have this thing? If I don't, look up, right? If I don't, it records it here. Rather, if I do, look up. There you go. So the delegation, if you have the item in the constructor, you provided a list, 1, 2, 3. It is 1, 2, 3. You're going to use those 1, 2, 3 in that list you provided it. If it doesn't, it's going to add it to your own copy of it. So it helps you differentiate between the one someone gave you and your own extension. And that to me, like, okay, it's in the chapter. I've explained it. Does anyone want to go over this anymore? This one is really, really, like, esoteric, if you ask me.
I'm done with it.
What's up?
I'm done with it.
You're done with it. Everyone's, yeah, that's a stupid one. Okay, name tuples. This one is actually kind of cool, right? So you can have these objects. We talked about this earlier. I forget with the example. I remember Ed did it because I remember thinking that is kind of laughable. But we went over these idea of positional parameters, right? You can create a function that takes one thing, two things, three things. At some point, it's taking too much crap, right? You create a function that takes 15 different things, and someone has to count 1, 2, 3, 4. Is this the 7th item?
Especially when you start using that function by putting empty things in.
That's even more obnoxious, right? So the reason why people often do that is because they don't want to use named parameters, or they don't know about named parameters, or they come from a language that doesn't have them, right? Or they don't know about these things called named tuples. The solution to that problem when we went over it in the class was, this is an object, right? You don't want to pass all of this different crap to a function. What you want to do is make an object with all of that stuff, and then you pass the object to the function. Right? Or you create a method that operates on that object. And we showed you the evolution of that as we refactored some of that stuff out. Well, this idea here, this name tuples thing, is if you want to quickly create something like a tuple, right? Let's go back to say what a tuple is, right? A tuple is this guy. If I say here, my t equals 1, 2, 3, foo, and then 5.0, that would be an example of a tuple. So if I want to print this out and I say my t, you can see all of this stuff here. But how do you get to the 4th and the 5th element of it? You have to remember that. You've got to know what that stuff is. So you have to know to go my t 5, my t 3, whatever. That is a pain in the butt. And when you start to create things that use that interface, it gets remarkably unmaintainable. You can see how this is really easy with a couple of things. But as you start to get to multiple things, it becomes more and more of an annoyance. So there's a solution to that problem. That problem is called name tuples, or the solution is called name tuples. And here's how you do it. From collections, import named tuple. From collections, import named tuple. Now we can do just like this. Point equals name tuple, give it a name, and tell it what the two things are. right? So point equals named tuple, give it a name, and tell it what the names are, x and y. Now what you can do is you can say here, k equals 0.54. Now when I look at k, you can see x equals 5, y equals 4, and I can say k dot x equals 5, k dot y equals 4. And if you do k dot, I think this will actually, it'll even return to you there, that it's a point. So this is actually just a method of creating a class. We talked about this earlier. We said at some point tuples become very difficult to maintain, and you want to create an object. You want to create classes. That's where you want to go with this, right? This is simply a shorthand syntax that does all of that for you. So if you find yourself writing libraries with tuples and then suddenly they become confusing, you can just use this name tuple method very easily, right? And you can continue to use tuples, but you can also use this. So now watch this. Now I have this x equals 5, y equals 4. But if I go down here to k0, what do I get? 5. K1, 4. That's just like the tuple. So it maintains compatibility with the tuple. It's still positional under the hood, right? But you can also refer to it in a method that's not ridiculous. Okay, so this is really a goodie. This one, I certify this. This is one you should know. This is intermediate Python. This is decent, right? This is where you're at. So when you start to use tuples, if you use tuples and you're not yet at the object point, this creates you a good shim that helps you get from point A to point B, and your tuples become objects, more or less. Okay, cool. Anyone get that? Anyone have any questions over this? Make sense? Okay. So back, we talked about it earlier, we said if you're using more than 5 elements in that tuple, you want to start to use an object. That's still true. Here's another solution for it. Okay. Gathering keyword args. Okay, so Python functions can be variadic, right? Which means that they can accept a variable amount of arguments. Okay, so let's say that you want to create something that always requires one argument, but the person that's calling it can provide it 2, 3, 4, 5 arguments, but you don't know how many there are. What do? Well, here's one method in which you can say, I know what I want to select for the first argument, and I want all of the other arguments to be stuffed into this args thing. Right? This is one method in which you can do it. You see the asterisk args? Right here? See how he's got that asterisk before it? That's a special syntax. And that means stuff all of the remaining arguments into that. Right? So let's say here that if I have def myfunc x args, and I want to do print x, you see that? I'm saying the above, I want to put the first element into x. And I want all remaining parameters, all remaining arguments that are provided to go into args. Right? You'll see this in most languages. JavaScript's got it. A lot of languages provide this. It's just a method for you to collect all remaining things into one tuple or one array. In Python, it's a tuple. They all come in as a tuple. Okay. Everyone kind of get that? See what we're doing here? This one's not complex at all. This is beginner level stuff. And it only is useful if you want a function that accepts, variable amounts of arguments, which is a very small amount of the functions you create. Hopefully none of the functions you create, but sometimes it's useful. Okay. Okay. Boy, he's getting really crazy with this one. To gather keyword arguments, you can use the asterisk. To gather keyword arguments, you can call the keyword gathering parameter. Does anyone use this? Has anyone used this?
Yeah, I actually use that a fair bit.
The
So-
asterisk?
Yes, I use that more than the other args, right? So it's like a dictionary of args, right? Where it says third equals 3. So you can name all of your arguments there. They can be there or not there, whatever. And they all the ones that have the equal sign there get magically turned into a dictionary and then sent to your function as a dictionary.
Cool.
That way you don't have to remember there's the connection between the argument and the parameter.
Sure.
That's right, yeah. Debug equals true.
Yeah.
You know, this equals blah. That type of stuff.
Fair enough, yeah. So there you go. I mean, I suppose I could see that being useful too. I mean, I've just never used it myself.
And so the way I do that is where you've got keyword args on the next line instead of print, I would just do get keyword args dot get whatever parameter like debug, and then you could even add a default parameter.
Let's show them with the very same example. That's a perfectly great example. Debug. I like that. So we're gonna do. We're gonna come back up and let's remove all that stuff. We're gonna go def myfunc, and we're gonna accept the same parameter x. And now what we're gonna do here is kargs. I think is what they're calling it. Is that like a convention?
KW. Yeah, you don't have to, but that's the convention.
Print x. Print KW args. And
The KWRs could be anything, right?
that's right.
Yeah, okay.
Debug equals 1. Oh, damn it. 5, debug equals 1. So there you go. So what it's doing is, you see this, how we're saying, just like Jason said, we're putting it here with an equal sign, debug equals 1. And what's actually happening is, the function is putting that into a dictionary called KWRs. So the asterisk means put all of the remaining things that have equal signs in them into a special dictionary. And you can use that for, I guess, flags you don't use often. Like maybe you don't always want to debug something, or you don't want every function to have a debug parameter, but you want the ability to tack it on at the end. You know? Yeah.
And you don't have to remember position.
And you don't have to remember position. So this is another method to get around static positions, which is always a bad idea. Cool.
Are you converted?
Yeah. Hey, I mean, if I ever, I definitely, I missed that one, but yeah, that's cool. And that's it.
So, folks.
Binomial coefficient, yeah, no. That's a horrible idea. Okay. Very cool. So that concludes Think Python. I think we are done, or it is appendixes, and my program hangs. If your program hangs, ask me, or read the appendix on that. Yeah. Cool. I think we're done here. And now we're going to, I guess, talk about where we want to go from here. Mention it in the chat room if you want to learn something, especially if you need help with something. If you want to continue with Python and you want to do the Automate Python book, drop a suggestion in chat. You know, we're going to definitely take that feedback seriously, and we'll be planning for 2019, you know, whatever we want to kick off with. Until then, we have a couple of Wednesdays at the very least until 2019.
May the force be with you.
And I'm going to look at the calendar here. So December 25th is Christmas, and the 26th is
Usually.
the Wednesday after. That's not really a holiday. So yeah, that means we have 3 more until 2019. Is it really?
In Swedish, it's a holiday.
It isn't. Huh?
Well, there you go.
There you go.
It's also.
it's Boxing
Isn't
Day.
it
It's holiday.
Yeah.
It's Boxing Day.
But that's the Canadians. Those are the same bastards that created pineapple pizza. I don't want no part of that.
More reason to observe it.
I'm kidding.
One part of the world.
So yeah, I guess we're not meeting on the 26th. The cPanel has it, as an open or whatever, then we're not doing it. So we have 3 more Wednesdays until the new year. No, 2 more Wednesdays until the new year.
Yeah.
Those 2, we're going to be doing lightning talks. So come up here with technology you're passionate about. You don't have to schedule it. You can drop a message in chat if you want. You can reach out to me if you need help with it. And please give us a presentation, 5 to 10 minutes, about whatever rocks your boat.
And for those of you who've been wondering if we actually do Linux at the Linux Users Group, there will be a few very Linuxy topics.
There we go.
Just in case.
Yeah, so yeah, we'll be doing that too. And if you want to get started with Linux, the recording has been saved. Didn't tell me where it saved it this time. Okay, I'll find it later. If you want to learn Linux, this is actually a great time to get started in that. Here's another thing that I don't know if we've given a shout out in this class. If you have an old laptop, it doesn't matter how old the laptop is. If you have an old laptop, even if it is a shitty battery, and it only turns on for 3 seconds, whatever the deal is, we get them quite frequently, bring the old shitty laptop up to us and we'll make it brand sparkly and new with some
Linux.
version of Linux, and we'll get you up with a programming environment, right?
Oh, like-
So you don't have to actually sink money into this. We can create you an environment that will get you started on the Linux side of things very cheaply.
Or we can create bootable USB drives that people can put into their Windows machines if they don't want to Linux drives.
We can do that, but I prefer nuking Windows.
Yeah.
I'm trying to get them off of it,
It's a gateway drive. Come on.
That's right. Very cool. We have one lightning talk scheduled for the night. Are we ready on that?